Indeed, this is what I'll be talking about, so I won't read out the title again. So this is work that was carried out in the context of the HST promo collaboration. So this collaboration has been pursuing for the last 20 years or so a wide range of projects that all have in common that we use proper motions to try to understand the structure and dynamics of structures in the local group. That has included the Magellanic Clouds. It has included a lot of theoretical work as well, including several things we heard about this morning. But we've really been trying to just exploit in general what we can learn from proper motions. So we have some 60 papers based on Hubble, some 20 papers based on exploitation of the wonderful Gaia catalog. And today I will talk about what has been our first paper of proper motions based on JWST. And in particular, I want to point out among our collaborators and key members, Mattia Liberato. He's the one that led the work that I'll be talking about today. But before doing that, let me briefly set the stage and give you a brief summary of other things we're doing. So this is a somewhat dated view of the local group. There's the galaxies we all know and love, and then there's the satellite systems of the Milky Way and Andromeda. And then if you're interested in dynamics, as we are, there's many things that you can study, and we have. So that includes the internal dynamics of the satellite systems, the motion of the clouds about the Milky Way, the motion, how that relates to the formation of the Magellanic Stream, as Gertina discussed, the motion of the Andromeda galaxy relative to the Milky Way, the motion of the Triangulum galaxy relative to Andromeda, and then within the Milky Way, the motions of halo stars, globular clusters, and stellar streams, among other things, and what that all tells us about the presence of dark matter, the formation of galaxies in general, etc. So the observational capabilities for such work from space are now these three observatories, and this landscape changed very considerably in 2018 when the Gaia DR2 came along. Before that, for about 15 years, Hubble was pretty much the only observatory that could really do credible, detailed proper motions in the local group as opposed to in the Milky Way. Gaia is fantastic for innumerable many things, but that will not be the topic of my talk today. One of its advantages, of course, is its full sky coverage, but one of its disadvantages is that it's limited to brightish stars, brighter than say 20. But if you want to do proper motions in the local group, really for them to be useful, you need to be even brighter than 20. So for practical purposes, outside of the sphere of the Milky Way, things get very hard. Hubble instead provides much longer time baselines, but it does so over a much smaller field of view. So it's not good for certain things, it is very good for other things. One of the benefits is it provides high accuracies to very faint limits, easily 25th magnitude. Now, Webb is now online as well. It provides similar spatial resolution and field of view as Hubble does. Moreover, because it has a much larger mirror than Hubble, you can in principle go much deeper and therefore get proper motions of many more objects in an object. And then when you average to say determine bulk motions or velocity dispersions, your square root of n advantage in reducing noise really pays off. There's big promise there. And in addition, Webb opens up extincted regions for study by using the infrared. However, because many things can now be done wonderfully well with Gaia, we are focusing a lot of our efforts now on the things that can't be done with Gaia. So what are those? So I'll talk about the LMC in a second, but there's a variety of other things that we're doing. So we're measuring the bulk proper motions of galaxies that are more distant. So we're measuring the proper motions of satellites of Andromeda. On the top right is a figure from a recent paper by Tony Sohn, but we have measurements for several other dwarfs at this point. We're also measuring the proper motions of isolated, distant dwarfs in the local group that are not associated with either of the two big galaxies, but part of the local group anyway. We're studying whether they're backsplash galaxies, whether they're on first infall, etc. And we now also have approved projects to measure proper motions outside of the local group. So we have cycle 31 Hubble projects for both LEO P and M81, which are sort of in the 1 to 3 megaparsec distance range. We're studying the internal dynamics of nearby dwarf spheroidals. My postdoc, Eduardo Vitrol, is finishing off a paper on Draco, where we have three-dimensional kinematics. But we also have additional data sets for Sculptor, and we'll obtain more data for Ursa Minor as well. We have JWST proper motions for the galactic center. that is in collaboration also with Jessica Liu's team on the West Coast, and that will allow us to study a variety of things. And then finally, we're developing techniques to combine Gaia data with other data, Hubble in particular, but that could easily be extended to Webb, to improve the accuracies of either observatory in isolation. So we have two codes now. One is called Gaia Hub, the other is called BP3M by Andres Del Pino and Kevin McKinnon, respectively. And just to show what such codes can do, on the right, you see a plot from Andres's paper for Draco. These are proper motions measured with Gaia in proper motion space. And this is what you get if you extend the time baseline by combining it with Hubble data. And of course, you get much higher accuracies that are easily visible by eye. So that brings me to the clouds. So, how can these observatories still change our perception of the clouds? Well, I've been working on the clouds for a long time. So this started with interest in the structure and viewing angles of the clouds, working on TUMAS and Dennis data with Maria Rosa, among other things. Then I started studying line of sight velocity fields using a variety of tracers. And then going on to proper motions, first with Nietzsche, looking at Hubble fields centered on background quasars that allowed us to measure the proper motion. Sorry, that was the wrong one. The proper motion of the rotation of the cloud. And then subsequently with the Gaia DR1, which provided, in essence, not new proper motions, but improved proper motions for Hipparchal stars, we actually verify the accuracy of the work that we've been doing for a decade with Hubble, showing indeed that our proper motions were correct, and the first infall hypothesis likely was correct as a result as well. But then, of course, in 2018, there was the Gaia DR2 that came along, and then the EDR3. And now we can trace everything from streamlines to beautiful velocity fields. And here you also see the improvements from DR2 to DR3 from Gaia collaboration papers. So what can we still add to this? Well, what we did is we analyzed data for a field that is about half a degree from the center of the LMC. And this is the calibration field that is used by JWST. So this is a field with a good stellar density of things that don't move too much relative to things in the Milky Way that can be used to calibrate the geometric distortions of the cameras. So this field was observed 16 years ago by Hubble, and then again during commissioning by JWST. And we analyzed those data to determine the proper motions that you get. And with this 16-year time baseline between these two different observatories, we get a median proper motion error at a magnitude of 20 that is 13 microarcseconds per year. And at the LMC, that's about 3 kilometers per second. And just for reference, the Gaia median error bar for its very brightest stars at magnitudes of about 10 is actually worse than that. So we can do better than Gaia 10 magnitudes fainter. But of course, it comes at the price of a very small field of view. And you can only do this for fields that happen to have been observed a long time ago, usually for other reasons. Here you see on the right magnitude, color magnitude diagram. Here you see the Gaia proper motions in this field going from magnitude 17 to magnitude 20. And here you see our proper motions. And you can just see by eye how much more accurate the proper motions are relative to what Gaia gets at these magnitudes. Now, of course, there are red supergiants in the LMC, and for those, Gaia gets fantastic proper motions, but they're much more sparsely distributed over the cloud. So what does this tell us? Well, so the CMD of this field, a CMD of this field is shown on the top left. One obvious thing to do is to separate the proper motion space into blue and red stars, which are proxies for young and old populations. And if you look at the young population, you see that the distribution is relatively narrow compared to the older population. And you also see that it has a lot of substructure. So this clump number 2, we actually identified coincides with a known cluster, not a very well-known one, but a 10 to the 4 solar mass object that just happens to sit in this field. We can actually measure its velocity dispersion to be about 5 kilometers per second. We know that, given its mass, it should be less than that, but that basically means our combined random and systematic errors are at the levels of kilometers per second at the distance of the LMC. Now, if you look at the old population, you get a much broader distribution that is smooth and doesn't really have much substructure. this really resembles much more what we measure in the Milky Way with Gaia, where you have lots of streams and substructure and different things that you could model in detail. So, if you could do things like this and actually understand them in the LMC, we might be able to learn a lot more about, what happened as a function of time in the LMC. But sticking for a moment with the older population, we measure a dispersion of 34 kilometers per second. And that is quite consistent with everything that we know from line of sight studies. So, Knut summarized various of them, but one thing they all have in common is that, depending on the tracer that people look at, people typically find velocity dispersions in the line of sight direction of about 20 to 40 kilometers per second, mainly depending on the age of the population. And that's really what you would expect, because we know that the LMC is about 1/10 the mass of the Milky Way in M31. They're all disk galaxies. And we know that the Milky Way and M31 have velocity dispersions near their centers of order 100 kilometers per second. So you would expect to be substantially below 100 in a galaxy that is substantially lower mass. However, our measurement is entirely inconsistent with what has been published based on Gaia EDR3. So this is the line of sight dispersion of carbon stars that I published 20 years ago, which is just totally flat with radius at about 20 kilometers per second. This is the dispersion of all populations published in Lurie et al. And they have different plots for different populations, but by and large, almost all of them have a very steep increase to the center of near 80 kilometers per second. And 80 kilometers per second just doesn't make any sense. Now, we now know it doesn't actually agree with our measurements, so it's probably just wrong. But it also doesn't make any sense because a galaxy like the LMC can't have a dispersion that high given its mass and given its disk-like structure. So what is almost certainly happening is that in Gaia, even after all your quality cuts, there is significant scatter that is due to crowding and blending. And that is not a surprise because that has been noted by other authors, and here's just 2 papers. But the Gaia catalogs published to date do not have detailed deblending treatments in them. So,
Really? You have about 1 minute Q&A.
So that means that it's not entirely surprising that you get added scatter, but it is important to take that into account if you do dynamical modeling, that you interpret such scatter not as purely dynamical in origin, because likely it's an instrumental effect. So to summarize, Hubble and Webb continue to enable unique dynamical studies of the local group and beyond, with very high accuracy to very faint magnitudes, but over very small fields of view. And Gaia is fantastic, let me be clear, but it should still be interpreted with some care in very crowded regions, because while mean velocity fields should not be affected by this, if you average over systematics, it you just average away. If you're interested in dispersions or scatter or disk heating or other things, you need to be a little careful with interpreting Gaia measurements as is, because it's really very hard to eliminate those systematics at this time. Thanks.
I think we have time for one question. I would encourage junior folks to ask questions.
Hi, Kat Barger, Texas Christian University. The proper motion measurements you're making are great, and now you're combining HST, JWST, and different instruments like that. Could you talk about how that can be troublesome? Like what kind of systematic issues or uncertainties are involved with combining these different telescopes?
You always have added uncertainties when you combine things from different observatories. However, we have done this before also with Hubble, combining measurements with ACS and Wide Field Camera 3. So, you do need ways to try to understand your systematics. So in this case, by actually measuring the dispersion of a known cluster, it at some level sets a limit on your systematics. When we can with Hubble, we try to do multiple epochs, and we use the same instrument at the same telescope orientation with targets on the same pixels, so as to minimize residuals from charge transfer efficiency, color effects, geometric distortion residuals, all sorts of stuff. But when it's not possible, it's not possible, and you do the best. But clearly, those systematics are acceptable. But let me be clear, there is a lot of machinery under the hood to get such results that tries to eliminate all these residuals. That would be a whole 1 hour talk in itself.
Thank you so much. Okay, so next up, I'll just introduce Oscar Jimenez Aranth while he sets up. He'll be talking about the large MCs dynamics with high resolution glasses.
Sí. Sí, espejo de esta. Thank you very much. Thank you very much. In this talk, I will present the results I have been doing in the during my PhD thesis. I'm Oscar Jimenez. I'm from Barcelona. I have been doing the thesis under the supervision of Xavier Luri and Mercè Romero Gómez, working with Gaia Data. Part of this work have been done in collaboration with some collaborations, some of them present here today. The title of my talk is the Large Milky Cloud Dynamics with High Resolution Glasses. So first of all, is okay, what do I mean with high resolution glasses? I would like to stress that this is twofold. The first one is talking about Gaia data, so observations, whereas the second one is related to embodied simulations, the Grado simulations that I will present them today. So here we have how Gaia observes the field of view of the clouds. This is not a picture, it's like real Gaia data plotted taking into account the photometry. So here the colors are the real G, BP, and RP fluxes. So as we have been addressing during these days, there is a clear sign of foreground contamination from the Milky Way. So the idea is that, okay, in order to study the Milky Clouds, we need to have clean samples. So we need to get rid of these Milky Way contaminants. One naively could think of using distances to separate both galaxies. However, as we know, parallax is not a good proxy for distances when working with the clouds, since they are very far away. So we need to think of something more sophisticated than that. So our first approach, one of the first projects I had during my PhD thesis, is using neural network classifiers to try to segregate LMC and Milky Way, LMC, SNC, and Milky Way stars. So what we have as an output of this machine learning classifier is a probability value, which will be close to 0 if the stars is highly likely to be of the Milky Way, or close to 1 if the galaxy is if the stars is highly likely to become to the LMC or SMC. In order to have a binary classifier, we need to define like a probability cut. In order, if the value of each star is larger than that, we'll consider LMC or SMC. If it's smaller, will be from the Milky Way. However, which is the probability cut that we decide to have, no? Depends. If we want to prioritize, for example, completeness, we will get like a small value, no? So in this way, we select like many stars will be selected as LMC. So we're having like a more complete sample for the LMC. So with the price of having probably Milky Way contaminants, we will not lose any LMC or SMC star. On the other hand, if we select a small probability cut, what we will prioritize is purity. So for sure, we are only going to have Milky Cloud star, but for sure, we are going to lose many of them. So when doing so, here, for example, to visualize how this classifier works, here is the XMC base sample, so with Milky Way contaminants. And when we get the more complete sample, we move to something like this. So we get rid of most of the Milky Way contaminants. And here we may see, for example, how the globular clusters in front of the LMC, they disappear even for the more complete sample. So this is one, but again, we can select different. And here also to highlight the quality of the data, we may focus on the bridge area, when here we can also see how Gaia reaches this part of the data for the classifier. And again, this is only one of the different samples that we can consider. And here what I do is to compare the different clean samples that we propose in our first article. So here we go from 80 million stars for the base sample of the LMC and 4 million stars for the sample of the SMC to smaller values depending on which is the complete level of completeness and purity that we want to have. Here, for example, as I was mentioned before, even for the more complete samples, the globular cluster from the Milky Way, they disappear, like 47 and NGC I don't remember the number.
88.
Okay, again, to highlight the quality of the data, no, we can select one of these samples, like the LMC complete sample, and make a zoom in. Oops, make a zoom in, and here we can see like different features, no, like the single spiral arm of center bar and so on and so forth. We focus to the more crowded region, as Van der Marel said. No, we still have some bias, but still we can recover like the absorption lines from the gas and so on and so forth. So this is part of the very first article I published during my PhD thesis, entitled "The Kinematic Analysis of the Large Magellanic Cloud Using Gaia DR3 Data." The method and the objectives were twofold. The first one is to get clean LMC samples, which I explained to you already. And the second one is to go to the in-plane velocities of these galaxies. That, thanks to Van der Marel, we know the transformations to go from the proper motions, line of sight velocities, to the in-plane, correcting from the systemic motions. So here what I'm showing is using Gaia astrometry for the different samples, how the radial velocity, which means if the star is moving inwards or outwards the galactic center, and the residual tangential velocity, which is the tangential velocity in comparison to the rotation curve. Will be positive if the star rotates faster, will be negative, it is slower than the average for a certain radii. So here we can see, for example, different the kinematic imprint, for example, of the bar, when we can see like the quadrupole and so on and so forth. So after that, what we did is to apply this very same technique from the machine learning classifier for the XMC that I already told you before. And we used these kinematic maps of the LMC in a paper that was published 2 months ago or so, to try to disentangle which is the bar pattern speed of the Large Magellanic Cloud, which means which is the rotation at which the bar pattern speed, the bar rotates. However, this is quite a long paper. I will not address it here. So in case you're interested, we can have a talk about it later. So this is for the Gaia data. Now we'll move to the simulations. That this is an article that now is in preparation. It is already submitted and in the referee process, which is entitled "Kratos: A large switch of n-body simulations to interpret the kinematics of the LMC disk." And here what we define is a large suite, as the mention said, like how many is a large suite is 28 simulations of pure n-body simulation of the cloud system. Why do we have 11 sets? And what do we vary between sets? Is like we are scanning the different free parameters of the system. For example, the total mass of the LMC has some percentiles, so we try to cover all of them for the different models. Also, the total mass of the SMC that we know that is quite uncertain, and so on and so forth. And for one of each sets, what we do is have 3 different models. The first one is an isolated LMC-like galaxy. So this way we have it as a control model. So in order to know if these initial conditions create, let's say, a bar, arms or not. The second one is the interaction between the LMC and SMC without the presence of the Milky Way. And the third and more realistic one is the interaction between LMC, SMC, and Milky Way-like galaxies. So here we have a video of one of the simulations of the suite. And here at the very center, we have the baryonic matter of the LMC and the baryonic matter of the SMC getting closer. This is one of the systems where the Milky Way is also taken into account. However, it's not plotted for the sake of visibility. And here now the galaxy still does not have a bar. And the first pericenter of the SMC creates it, also with the 2 spiral arms. And the second pericenter, what we create is an off-center of the galactic bar, as Gurtina said previously, and also the creation of a single and broken arm. Here we have it. We also run these simulations like for positive time, which means like looking at the future. But again, this is only one simulation. Remember, those are 28 here is like the present time. So here we can have like different features if we compare it with real data. Like for example, like the off-center bar, 2 arms, like a single arm which is broken, so on and so forth. But again, this is only one simulation, but we have 28 different simulations, and we have like very different features on this LMC-like galaxy. Like for example, flocculent arms with a strong bar for some isolated galaxies. We have grand design arms with a strong bar. We have flocculent arms without a bar. We have grand design arms with a very weak bar, if any. ring-like structures after the interaction. For example, as I was saying before, no single and broken arm and an off-center part. This is the galaxy scene face on. However, we can see it also edge on. And we may see for the non-interacting disk, like flat and thin and well-behaved disk. However, we also have distorted and thick disk. And for example, warp and flares. So again, this is like, the idea is to compare this with observations, and one of the observables we have are the kinematic maps. So we can move from these density maps to these kinematic maps, again on VR, and the residual tangential velocity. Again, this is like a single snapshot, but we have like the whole temporal evolution. So in here, my very last video, I want to show how, as the time evolves, the different kinematic maps changes. And we can try to compare this with the real observables. And here the XMC is not plotted, so you will not see like the interaction, but more or less like now you will see in the edge on galaxy that now it starts to get distorted. So this is how the effect of the interaction of the SMC with the disk of the LMC. Now comes the secondary center, and so on and so forth. So yes, this is all I wanted to say today. Just mentioning that the images I have been showing are in my personal webpage. So the idea is to share within the community. So feel free to use them in any talk or whatever. So thank you very much.
Thank you. Are there any questions? Take this moment to scan the QR.
Thank you for your talk. My question is, in your models, did you include different masses of the Milky Way?
Yes, we scan, like the fiducial model has 1 × 10^12, but we also try to make like a less heavy Milky Way and a heavier Milky Way also. Yes, it's one of the 3 parameters. We also try to, because the fiducial model has a Navarro-Franken-White distribution for the Milky Way, we also wanted to see what, if considering like a point like Milky Way, which is the effect on the simulation, and I can tell you this a lot.
Hi, Camila Navarrete from Observatory de la Côte d'Azur. I'm curious about the simulations where you show the distribution, the density distribution. What is the range in dimension, I mean, in kiloparsecs that you are covering by the simulations?
Yes. I think that the radius of the LMC is more or less 6 or 8 kiloparsecs. Now I don't remember, but more or less like this.
I saw a few hands come up over here. I don't know what we're doing. Hi, thanks for the nice talk. I was wondering if you could say more how you initialize the orbits, or do they match the real orbits, or? Yes.
The initial conditions were the ones given by Scott in his article on the Magellanic Stream. However, since we are using like pure body simulations, they don't have gas that he considered aerodynamics. There are like some different changes in the orbits for our fiducial model. Also, when changing the different mass, for example, the total mass of the LMC and SMC, for sure it has an effect on the orbit. So our idea is to have like LMC-like, SMC-like system, and not to, like the main idea is to talk about more about the different features that may have in the internal kinematics, rather than trying to know which are the correct orbits. Yes.
All right, thank you so much. Okay, next up, we have, oops, should I move? Yeah, okay. So we have Slater Odin, who will be talking to us about searching for the edge of the LMC.
Hello, testing. Yeah, hello, everyone. I would first like to thank the organizing committee for allowing me to come out here and give this talk and be a part of this conference and learn from all of you greatly intelligent people. So yeah, I'm a second year grad student at Montana State University, working with David Nidever, testing the hypothesis of whether smaller local group galaxies host accreted stellar halos. And in doing that, I'm searching for the edge of the LMC. So I think, as we are all aware, a very important tool that we have in our toolbox to study galaxies is to ask the question, how does stellar halos form in galaxies, and study the most loosely bound stellar counterparts to galaxies. And we have great observational evidence that the Milky Way halo is very substructured, which is reminiscent of past stellar accretion events with smaller dwarf galaxies. But the question still remains, what about smaller dwarf galaxies? Do they also host stellar accreted halos? Well, we don't really know, but we do know, as we have been seeing today, that the LMC and SMC are interacting and have produced these long gaseous streams with stellar counterparts now. Yeah. And in 2006, there was a paper conducted when I was only 6 years old and not thinking about any of this, studying the Carina dwarf spheroidal galaxy that incidentally discovered a group of stars that more kinematically belonged to the LMC. And they nominally called this the 330 group based on its heliocentric rate of velocity. And this group is better fit with a spherical isotropic halo rather than just an extension of the LMC disk. So that is pretty interesting. Since then, we have acquired an amass of data that tells us a bunch of different things. One, the LMC is much more extended than previously thought and has significant substructure in its periphery. So yeah, so I am primarily working with MAPS data, and in this particular talk, I'm going to focus on this northeastern section. I also use Gaia DR3 data in this analysis to help complement the MAPS data. And there's a couple of different goals that we have set out. One, we want to help bridge the gap, so to speak, of the LMC disk to the out in the periphery to this 330 group and beyond, and search for more potential LMC stars out to projected distances of 28 to 29 degrees. And I need to mention, I nominally called these hydra-Mike stars, hydra-Mike fields up here in the left-hand corner, because they have their spectroscopy done with the Hydra and Mike spectrographs. Okay, and this is just kind of a nice zoomed in version of this northeastern section that I'm working with that shows the nice spectroscopic data that I'm working with. So what we've done is we've made a number of selection cuts to be able to target LMC, red clump, and red giant branch stars. We've made CMD cuts, astrometric cuts, parallax cuts, proper motion cuts, log G, T effective cuts, and I think probably the most important one to help eliminate Milky Way foreground contamination is a radial velocity cut. And on the topic of Milky Way foreground contamination, I've taken a deep dive recently into the expected Milky Way foreground contamination through running various Bayes-Son Milky Way model simulations and Gaia DR3 queries. But unfortunately, Gaia does not give us great velocity information. So we don't have much information of the expected rate of velocity from Gaia. However, running Bayes-Son model simulation on the same square degree coverage of these hydromike fields and the same approximate area of these fields, this model suggests only one Milky Way halo star with the expected heliocentric rate of velocity of greater than 300, which is good news for these fields. The Milky Way contamination is minimal to negligible. All right, so in proper motion space, this is what the bright Gaia RVS, primarily RGB stars look like. And I think there's a number of different takeaways from these, and they're color coded by various different physical parameters. One, we see a rather tight clustering in proper motion space, as can be expected. However, as we move further out from the LMC disk, as we can see in this top left plot, that's color coded by LMC radius, we see a greater systematic change in the proper motion. And this is in agreement with the MAPS data of the Northeast section. Again, we see a rather tight clustering closer to the LMC disk, but a greater systematic change in proper motion space as we move further away out in the periphery. So the stars of interest here, right, are these hydromike stars in this 330 group. And this background contour in these plots is that of the MAPS Northeast data. And again, I think there's a couple different takeaways from these. I probably won't be able to touch all of them, but I want to touch three. So we see a good chunk clustered around this expected proper motion space from the MAPS data in the outer periphery, right? So this is good news. We have potentially discovered RC RGB stars out to these great distances. However, there's something going on kind of in this left-hand corner around 0, and that is where we expect kind of the Milky Way halo stars to reside in proper motion space. And up there in the top left-hand corner is where the thick disk of the Milky Way primarily resides. So the potential for contamination there is more significant. All right, so lastly, what I've done is I've taken use of Knut Olsen's kinematic model, and I've fit these stars with various position angles, LMC position angles in the LMC disk. And you can see it is color coded by position angle. You can see it's not a great fit to the data, which may or may not be surprising. I think this could be reminiscent of the rather extreme or different kinematics in the periphery of the LMCs. And so moving forward, we would like to take use, or I would like to take use of the SDSS5 BOSS spectroscopy data. You can see a much more contiguous coverage of this northeastern periphery of the LMC that I think we can exploit and help validate some of our conclusions that we've made here. And with that reaches the end. I just want to say thank you for listening, and I can take any questions.
Is it on? Yes. Okay. Any questions?
Hi, Cal Barger, Texas Christian University. Excellent work. It's exciting to see how far extended the LMC goes, and it's interesting how much more we still need to know about our neighbors. So I'm thinking, like, in order to do our neighboring galaxy justice, to really map it out, there's this piecemeal work that's kind of being done, this little location, this little location, this little location. But how do we how do we do a good job of just getting the whole thing? I'm thinking like if we use Roman, that'd be great because then we could get deep imaging. But at the same time, I think then the Milky Way contamination doesn't go away. So, because it looks like you're relying a lot on proper motions and possibly kinematics with like BOSS and so forth. So is that the thing? Is that no matter what we do, it'll be painstaking because we either need the proper motions or kinematics to separate the two?
Yeah, I think that's a good point. I am very excited for what the future holds for more data to be able to help reach these conclusions. But primarily, yes, it is the kinematics that we are using to help distinguish whether or not they belong to the LMC.
Any questions from this side of the room? Back of the room. Thank you so much. Okay, next up we have Camila Navarte, who will be talking about tracing the interaction history of the MCs using stellar substructure at their periphery.
Thank you. I'm Camila Navarrete. I'm a postdoc at the Observatory of the Côte d'Azur in Nice. And I'm very happy to be here so I can share with you the results of my last paper published last year regarding the 3D kinematics of stars at the periphery of the clouds in some of these stellar substructures that we have been seeing in previous talks, and how we can use that information to put some constraints on the past orbital history of the clouds. So I think given all the talks, I don't need to go into much detail, but more or less we know that the clouds have been interacting, and because of that, there is evidence in the morphology, in the gas, and I think we can all agree that there was a last encounter around between 100 and 200 megayears ago. And this plot was also shown by Gurtina, in which, depending on the Milky Way and LMC masses and the relative velocities of the clouds, more or less there is an agreement on the time and the separation of the clouds during that encounter. But beyond, sorry, I'm going to move. Beyond that point, it's not that easy to constrain the number of encounters. And depending on the models, we have different orbital solutions. Here I'm showing two examples from Patel. It's Patel. Yeah. Here in the dashed lines, you see the separations between the LMC and SMC for 3 different LMC masses. So there could be between 2 up to 4 times where the clouds encounter in the last 6 gigayears. But other works like Lucchini et al., considering the gas and the Milky Way corona and the clouds corona, found a very different orbital solution that you can see here. So, but what about the stars at the periphery? The stars at the large distances from the LMC and the SMC are more easily perturbed by tidal interaction. And thanks to wide field surveys, photometric surveys, and now Gaia, we have this panoramic view of the outskirts of the clouds. And here you can maybe identify some of these stellar substructures, the arm in the north, some stars towards the east, and other stars in the southern part. But the origin of these substructures is not straightforward to determine just based on the spatial density. So in the very early studies of this northern arm, some authors were able to reproduce the feature due to the interaction of the LMC and SMC in isolation, or due to the interaction of the LMC with the Milky Way alone, or using the 3 potentials. So in order to get a better idea of what's the origin of these substructures, we need kinematics. We need more information, of course. And that's why I use a very particular tracer in my work. We have been discussing about having distances, well, I use Myra variable stars. These are pulsating stars like Ara Lyra or Cepheids. So we have distances from periodic velocity relations. They are very luminous. You can see with Gaia magnitudes around 15. So the proper motions from Gaia are relatively good. They have large amplitudes in their variability, so we can isolate them and reduce the contaminations from Milky Way giants. And they are good tracers of disk population. So my work in the paper was focused in the selection of Myra candidates based on Dison et al., based on Gaia photometry, TUMAS photometry, so very red objects, with variability cuts based on Gaia, so the very specific parameter space. And in the work from Dison et al., they also take into account the proper motions, so we can clean the sample of Myra candidates and recover a map like you see here in your right. So there are not so many because it's not a very numerous population, but they more or less trace exactly the same substructures that we can see, for instance, in this map from Gaia. So there are stars following what is called Mackey Stream or Northern Tidal Arm. It has different names depending on the paper. Other stars towards the east, what is called the Eastern Excess or Interstellar Substructure, and in the south. So for these stars, we have a relative good distances, proper motions, but we were missing the radial velocities. So we did a small campaign. We went for the Cosmos spectrograph at Cerro Tololo, and we got the spectra for around 40 Myra candidates, because we can also have other pulsating stars in the same color region. Here for reference, I'm showing in this map other works that were mentioned during the talks. There are the study of Cheng, I'm missing the G, in which 6 apogee fields were used to study the kinematics, 2 in the north and 4 in the south, or the different papers from Culinan that study different fields around the clouds, mostly tracing the northern arm and the inner 10 degrees around the LMC. My targets are those in purple, green, and red, and they are mostly concentrated in the east part, and they are between 10 up to 20 degrees from the LMC center. So as I may not have a lot of time, I'm going directly to the results. So including the information we have on positions, velocities, and proper motions. And I compute the 3D kinematics, taking into account the systemic motion and all the equations we need to take into account. And this is more or less what we got. Here is the circular velocity of the stars, the in-plane radial velocity, and vertical velocities. And what we can see here is that stars at up to 15 degrees from the LMC center have a circular velocity more or less consistent with the value of the LMC rotation curve. But beyond that, there are large disturbances. Here, the stars that are with a box, well, with a square, have very large disturbances from the 70, 80 kilometers per second value from the rotation curve. But most of them are moving like LMC disk stars. But when we see the radial motion and the vertical motion, there are very large disturbances. Again, they are larger as we move outwards. And overall, our results, we also study metallicities, are in the same line as other previous work, in the sense that stars in the northern arm and the east part are probably related to LMC disk stars that were perturbated. And we can also consider that is expected. For instance, these are the results from Culinan for a numerical simulation following the interaction between the clouds during 1 gigayear. And here is the mean radial motion and the mean out of plane motion. And you can see that as you move farther out from the clouds, the differences or the velocities get more disturbed. So in the last minutes, I'm going to explain how we use that information and numerical simulations to estimate or have an idea of what kind of orbital interaction history between the clouds can reproduce our data. And the simulations were performed by Dennis Erkal, which I think is connected through Zoom. And very briefly, we could take into account the potential of the Milky Way, the LMC, and the XMC. And we use the present day positions and velocities. We rewound the orbit 2 gigayears in the past. And then we include LMC disk particles. And then we made the system evolve. So in the end, we had 400 model realizations. In each of them, we have 2.5 million LMC tracer particles. And we compare the present day positions, velocities, proper motions of the particles and the MIRA data. So at each position on the sky, we compare the mean motion of the particles with the observations. So in the paper, we present several statistics. Here I'm showing just one. So in the plot, you see the look back time and the minimum disk crossing of the SMC with respect to the LMC. So to give you, to explain it better, here you can see in the top panel, the look back time and the distance of the SMC with respect to the LMC disk for a group of these 400 simulations. So each simulation has a different orbital history, different number of times when the SMC crossed the LMC, different distances, relative distances. And when we compare the data with the simulations, here this color bar is a representation of the chi-square, how similar are the data with respect to the simulations based on everything, proper motion, distances, positions, radial velocities. You can see that there is no perfect match, but the ones, the simulations that are in yellow, which are inside the red box, have the better agreement with the data, and they are all of them very similar with a encounter, like the closest encounter 1 gigayear ago. And the 40 simulations, more or less, have this kind of orbital history 3 times when the SMC crossed the LMC disk at these particular times. This is the mean value based on this group of simulations. And the sigma is the dispersion on the time based on these 40 simulations, independent realizations. These are the distances between the LMC and the SMC. So the disk crossing at around 1 gigayear ago seems to be very, very close between the SMC and the LMC. But as I said, the match between the observations and the simulations is not perfect. You can see here an example for one of the simulations, the mean vertical velocity and the mean radial velocity, and the data, more or less, they are in agreement, but there are some cases where they are not. But I guess, or I feel that the results are interesting because these times are coincident with the 3 times of the peak on the star formation history again. So I think they are going in the same direction, although of course we need more data maybe in the at very large distances to have a more robust conclusion. So just to finish, variable stars are very useful tracers because of the distances, although they can be challenging. They are pulsating, so the parameters, the metallicities are hard to get sometimes. In the case of MIRA variables, in the paper, there is a long discussion because there are different types, carbon-rich, oxygen-rich, some stars pulsating in the fundamental mode, first overtone, so it's not that straightforward. But based on the radial velocities, we were able to get this group of simulations that seems to give us the best agreement with the data. So if you have more questions, you can, of course, ask me or go to the paper. Thank you.
Thank you. Are there any questions?
Thank you for your talk, Yong, Zhen, RPI. So I think a few slides ago, you talk about the 3D kinematic structures of the NMC disk, and you show some stars that are not consistent. I wonder if you know the age of those stars.
Not, but that's a very interesting question. We try to do that because for Myra variables, there is a relation between the period and the age. So we could have an estimate, but some of the stars don't have a really good period determination. So we haven't tried to get any ages, but that's very interesting. We were very surprised because they are very different in velocities, like 300 or something. But all the other properties like distances, they follow the period luminosity relations. So they seems to be not outliers, but real measurements.
Thank you. You have a question? Sorry.
Thanks, Camila. Great talk. So when you feed the data and compare to the simulation, when you compare in the data, in the simulation, you also get the same tidal features as in the data, or?
You mean in density?
Yeah.
More or less. Not all the 40 simulations are exactly the same, but in most cases, we recover the northern arm and part of the eastern structure, but not like one-to-one. So they were there, but not exactly at the same position. So in the paper, there is one example showing the density distribution of one of the simulations. So it's a good agreement, but it's still not perfect.
Okay, great, thanks.
Kat Barger, Texas Christian University. So I'm wondering, so like looking at your interaction timescales as far as like the most recent interactions and further, for the most recent interactions for simulations and observations, I hear numbers that are anywhere from the order of like 100 million years ago to now. I think yours was closer to like 350.
Yeah.
And I was just wondering if you could speak a little bit about the recent interaction and like the uncertainty of it, because people just have numbers all over the place. And yeah.
Yeah, I mean, we use as a measure of the uncertainty how different are the simulations that have this encounter. But of course, this value is very different to other ones that are 200, 250, 150. So, I mean, it's hard to tell because we are constrained to the number of simulations we did, what we took into account. But I think it's something that we need to we consider. I mean, I'm not saying that these are the final times, but I'm not sure. Maybe if someone is an expert on this, can also give us more information about what is this exact time. So I think at least all the simulations that are independent have this value around with a dispersion of more or less 20 mega years. But also, if this is the time of the SMC crossing the LMC disk plane, if we look at the pericentric passage, is 260, so maybe going in the same direction.
Knut Olsen Warlab, thanks for the talk. Given what Gertina said about when you have a close interaction and body models might be needed to probe the all the nonlinear effects that come, and that we now have a fairly large suite of models. It sounds like from Kratos, from your set, from Gertina's set, from others. Do you have a sense for how important including or not n-body modeling effects is on, for instance, the timings that you reported?
Yeah, I don't have a feeling, but for sure, this is, as Gertina said, not the right way to do it. Like if we want to be very consistent, and we need to take into account the n-body effects, but I don't have a sense how important it is. What I know for sure is when I compare the simulations with the data, the most important information was in the radial velocities. So that's something that makes a difference if we want to compare the simulations. but of course, more simulations, and also very interested in the simulations from Oscar. That would help for sure.
Thank you so much.
Yeah, no, really is. No longer tiny.
Okay. All right. So now April Horton is going to talk to us about the tale of winds, tides, and ram pressure stripping. I love that title. Characterizing the properties of the Magellanic Stream.
Great, thank you very much. Like she said, my name is April Horton, and I'm a third-year graduate student at Texas Christian University. And today I'll be presenting on some of my master's work that I completed last fall. And specifically, I am looking at the Magellanic Stream. And as was mentioned earlier, and a lot of the different presentations, is that as galaxies interact with each other, the material on the outskirts is torn and swept away by different processes that are occurring in the environment. Here is an image where the LMC and the SMC is there with the Milky Way in the center, and the long pink ribbon in the back is the Magellanic Stream. And it's likely that as the gas is being pulled out of the galaxies, it can be pulled into a trailing stream, often flowing out of the galaxies. One of the most prominent examples is the Magellanic Stream in the night sky, and that is because it is roughly around 140 degrees. It spans that much across the sky, and it also has about 10 to the 8 solar masses of neutral hydrogen mass. So beyond general characteristics of the Magellanic Stream, it also is divided into 2 separate filaments. And these filaments are separated in spatial orientation, in kinematics, and then also in chemical composition. So here's an image showing the 2 different filaments. One has a higher metallicity of about 0.5 solar, coming from the Richter et al. 2013 paper. And then the other one, the lower metallicity filament, has a metallicity of about 0.1 solar, coming from the Fox et al. 2013 paper. For my project, I am specifically looking at the higher metallicity filament. And because these 2 different filaments have different chemical compositions divided, they are separated also in kinematics and spatial orientation. It is assumed that these filaments have different origins, with the lower metallicity filament likely coming from tidal interactions stripping material from the SMC. And the higher metallicity filament is assumed to have originated from the LMC, and more specifically, an active starburst region known as 30 Doradus. Here's an image from a paper from my research group that we are working on publishing pretty soon, talking about a little bit of how the Magellanic Stream can be formed. So we have the LMC up here, the SMC, and the Milky Way up there. We have an example of a line of sight for the targets that we're looking at. And as the LMC moves through the Milky Way's halo, there are apparent headwinds or ram pressure stripping that is likely to pull that material that the LMC is ejecting, like through galactic winds, through starburst regions. And that material can be pulled into the Magellanic Stream flowing behind it. So for my project, I am looking at UV absorption line spectroscopy, trying to determine the properties of the Magellanic Stream. And we are using the Ulysses data set. So here is an H1 or neutral hydrogen emission map with all of the sight lines from the Ulysses project highlighted in one of the black stars. But I am looking more towards the 30 Doradus region, or more specifically, this region over here. And I have selected 4 different sight lines that are near 30 Doradus, but also align with the predicted velocity of the predicted location in galactic longitude and latitude of the Magellanic Stream. For our project, we utilized the gas and gas cap for our H1 21 centimeter emission, along with the Ulysses data set for the UV absorption. And for more information on that, we have 2 more talks at this conference, one by my advisor, Dr. Kat Barger, talking about the Ulysses data set, and then one by a postdoc in our research lab, Dr. Suraj Patel, talking more about the outflows from the 30 Doradus region that may be funneling material into the Magellanic Stream. So the very first step in my project was looking at the H1 data to kind of see if I could identify the Magellanic Stream in the emission spectra at all. So I made these position velocity maps where we have the galactic longitude on the x-axis and the velocity on the y-axis. And I have on the right-hand side, the gas and gas cap emission kind of turned on its side to show where the peaks in the emission are. So this line right here, this horizontal line, is the predicted velocity of the Magellanic Stream coming from David Nidover's paper in 2008. And we can see that we have 2 different peaks in the emission, one that lines up pretty well with this chunk right here, and one that lines up with this emission band up here as well. And because the top emission band lies very, very close to the predicted velocity there, I am assuming that the lower band is the LMC's disk and the top band is the Magellanic Stream. And to provide a more kinematic constraint on the bounds of the LMC's disk and the Magellanic Stream, we performed a Gaussian decomposition on the gas data. And then we also estimated by eye from these position velocity maps where we expect the Magellanic Stream to be located. So for this example, I would say that the Magellanic Stream is somewhere between like 265 to about a little less than 300 kilometers per second in our UV data. So then we turn to the UV spectra from the Ulysses sample. And just from the kinematic bounds from the position velocity maps, we can identify different features in the spectra, where we have the Milky Way at about 0 kilometers per second, the LMC's disk there, and then the Magellanic Stream highlighted there. And from our spectra for 4 different sight lines, we find that the Magellanic Stream is visible in low ionization species, such as like iron, sulfur, silicon, aluminum, and phosphorus across all 4 of our sight lines. And then just a couple of the sight lines had features in nickel to sulfur 1 and carbon 1. So to get more information about the properties of the Magellanic Stream features, we used the VoigtFit Python software where we performed a VoigtFit profiling technique where we can determine properties like the column densities, the kinematic widths, and the central velocities of these features. So for this talk today, I'm going to be specifically highlighting more of the kinematic widths and the central velocities results that we were finding. And to help visualize this a little bit better, I've created this plot where we have our 4 different sight lines here. And on the x-axis, we have the velocity. And on the y-axis, we have the offset from 30 Doradus. Here in this pinkish color is the velocity range of the LMC's H1 disk from our emission. And similarly, we can also highlight the Magellanic Stream where it's located in velocity space as well. And now I'm going to overlay the predicted velocity again from David's paper, just showing where it is relative to our 4 different sight lines. So now I will add different components for the features that we are looking at. So we found our sulfur 2 highlighted in the red boxes here, where the width of each box represents the full width half max of each of our features. We see that for each of our 4 sight lines, there are 2 different components, sulfur 2. We can also overlay the aluminum 2 in green as well, and then the aluminum 3 just as an example. And what this plot is showing is a quick visualization of the kinematic range of the Magellan extreme features. So for the two sightlines that are closer to 30 Doradus, they have components that are at a much, or not much higher, but they're at a higher velocity than the two different sightlines that are farther away. We also can see that the aluminum 2, one of the aluminum 2 features here is being blended between the Magellan extreme and the LMC disk. Need to consider when we're recording our measurements. And then we can also see that the full extent of where we should be looking for the Magellan extreme in the UV data is between like 235 to about 350 kilometers per second. So in conclusion, we find the Magellan extreme on the near side of the LMC in our absorption features for different low ionization species, and also between a velocity range about 235 to 350, depending on how close the sightline is to 30 Doradus. And going forward, we hope to incorporate additional sightlines along the Magellan extreme to help better quantify the results that we're finding. Right now, we are in the process of looking at these 4 sightlines that are highlighted by the green stars, trying to see if we can identify the features in the UV spectra as we have already found them in the H1 emission. So with that, I'm happy to answer any questions.
Wonderful, thank you so much. Here, are there any questions?
Thank you. Beautiful work. I love your cartoon. And so I wonder, can you explain why you choose these 4 stars? Because I know there are a lot more stars in this region from the Ulysses data set.
Yeah, very good question. So I selected these 4 sightlines specifically because they are observed with the STIS E140 and E230 M grading. So they have a lot more available ions to look at in that specific range. I may be incorporating some cost data, but that is a little bit more difficult to work with in the STIS, but these are just STIS sightlines at this point.
Annalisa Techia from ISO. Very nice talk, April. Very exciting to see. Given that 30 Doradus has such a special population of stars, like very massive stars, I'm really curious to see if you can measure any peculiar abundances in the gas due to this peculiarity of the region.
Yeah, that's a good question, which Dr. Siraj may be talking a little bit more in his talk. I have, for my 4 sightlines, initially the closest one I had was A, but it was hard for us to determine abundances because there's a lot of saturation between the LMC's disk and the Magellan extreme. So it was hard to find 2 consecutive ion transitions that would work for our project. We do have some really rough estimates, but I hope with these additional 4 sightlines here, we can better constrain that information.
So could you say a little bit more about your future work?
Yeah, so right now we're just trying to find other Ulysses sightlines that are near the Magellan extreme or show signatures in the Magellan extreme in the H1 emission. And then once we have the additional sightlines we are going to be including, we're just going to run through the same process where we're going to identify the LMC's disk and the Magellan extreme and the UV spectra. And then we're going to perform the void fit analysis, determining like column densities, kinematic widths, and central velocities of those components.
Looking forward to it. All right, thank you so much. Okay, so for the last talk of this session is Erica Chwalik, who will be talking to us about mapping the edge of the MC stream.
Hey, yeah, so as she said, my name is Erica Chwalik. I'm a graduate student at Montana State University working with David Nidever. And yesterday a point was brought up by Kat Barger for one of the things that we need to know to constrain the tidal interactions between the LMC and SMC, and that is the length of the MS stream and, you know, distances and other things that can come from that. So I'm hoping to make some headway on that point today, talking about my project. So great that April went before me, so you guys have already seen a little bit about the stream. But just to sum up the things that are important for my project, the MC stream is a trail of H1 gas left behind the XMC system. It's compact high velocity gas, and high velocity here means anywhere between negative 250 kilometers per second to around 500 kilometers per second. And these velocities follow a gradient along the trail of the stream. So closer to, let's see. There we go. Closer to the LMC and XMC, we're getting closer to negative 250, so some of those lower magnitude velocities. And down towards the end, we have closer to negative 500 kilometers per second gas. And that'll come in handy later. So why is this important? I know this is a conference related to why all of this is important, but I just want to go over some specifics for the stream. So we can track the evolution of the XMC system and friends through the length of the stream, the different tidal tails in the stream, and also some relationships with local dwarf galaxies that might be related to the XMC system. This also helps us clarify our own galactic evolution here in the Milky Way. So obviously the Milky Way is accreting gas off of dwarf galaxies historically. This system, the XMC system, is a great lab for studying that. We can actually see individual stream components. So this is a fantastic opportunity to study the way the Milky Way interacts with dwarf galaxies. And also we can constrain the mass of the Milky Way. This has been pointed out by a few people at this point. I think most recently Craig et al. 2022. And that's important because historically our mass estimates have been a little all over this place, and this table's a little bit old now. This is from 2016, but these are kind of everywhere. And now that we know that the LMC is fairly massive, about 1/10 of the mass of the Milky Way potentially, it's pretty important that we nail this down. And we can do that by looking at the length of the stream. So now that I've hopefully convinced you why it's important to know things about the stream, especially how long it is, I kind of want to talk about the history of the stream itself. So historically, the stream was around 100 degrees. So we had the large Magellanic Cloud, the small Magellanic Cloud, and then about 100 degrees of stream ending around here. And keen-eyed viewers may notice there's a whole bunch of gas out here that looks like it could potentially be part of the stream. And great, yeah, Nidever et al. 2010 thought that too. So they mapped the gas between the known stream at the time and a survey, ETO4, which is all that gas out there, to find a connection here and hopefully extend the length of the stream. And they did find that this connection was real. They found this spatially, right? So this top plot here shows the spatial connection. But it also continued in velocity. So I mentioned that gradient earlier that would come back up. Here's that velocity gradient that the stream follows, and plotting the gas in that region over the velocity gradient, we can see that it does actually follow that, which is great. And another thing that came out of this was that on top of the stream now being out to 140 degrees, which I think somebody mentioned earlier in their talk, that's the currently agreed upon length. We also have this inflection in this velocity gradient around 120 degrees. So that's all well and good, but it kind of looks like this could go onwards, right? And in fact, I kind of hid part of this graph, and that is this cloud way out here. So this is part of a different survey, and it kind of looks like it could continue on this gradient rate. So wouldn't it be great if somebody had mapped this area between here to see if it was continuous? Good news, we did. And so this is the survey that we did right here. So here's the original stream gas. Here is the new compact high velocity cloud that could be part of this stream. This was a pretty sensitive survey. So it was done on the Green Bank telescope. Again, these are H1 21 centimeter observations. So it was 435 hours on the GBT, 300 square degrees, and it was 5 times deeper than the previous survey I mentioned, this one that connected this gas. And that's because out at the tip of the stream, the gas is super dispersed, right? So it's very hard to detect out at these lengths. It takes a lot of telescope time, which is why we're not just going all over the place looking for detections at the end of the stream. So here are the preliminary results of that. So this is just a column density plot for the velocity range of the stream. So negative 550 to negative 250 kilometers per second. And there's a couple interesting things we're seeing here. So I kind of labeled them. So there's 3 kind of distinctive compact high velocity clouds. So again, that dense cloud that is around the velocity range that we care about. And there's also this one that I've labeled IC10 up top. And that's because it is the dwarf galaxy IC10. It just happened to be in this area, which is pretty cool. But it's not exactly what we're looking for. So it's good that we know that it's there. Not exactly what we're going to use to map the stream now. But to know more about these clouds, to confirm that these actually match that velocity gradient, right, we need to know more about the signals. So when we're seeing these signals, oftentimes they overlap with each other. So it's good to do Gaussian decomposition on these. But 435 hours of observing is a lot of spectra to go through by hand. So we used a Gaussian decomposer for this. So we used Gauss decomp. So this was made by David Neidever. And this is just showing some examples of some synthetic signals I put through Gauss decomp and the output from Gauss decomp that it takes those. So in this top one, I wanted to show a very small signal because oftentimes we do see small low signals that we're going to have to potentially detect and differentiate from noise. And that was able to be detected by Gauss decomp. Down here, we have a compound signal, so 3 different parts overlaying each other. And fortunately, it's a slightly worse fit, but it gets most of the components, which is perfect for what we're doing here. So we used Gauss decomp to decompose all our signals. And if you're interested in using Gauss decomp for your projects, that's now up on GitHub in Python. I believe it was originally in IDL, but that is now usable in Python. And here are the results from that. So initial results, I have mapped velocity to color here. So we're looking kind of for these lower end velocities, these negative 450, negative 500, right? So out here we have this cloud that ended up being closer to negative 250, negative 300. So maybe not quite what we're looking for. And of course, IC10 is up there, and I put that in our area of interest, which I've kind of circled here in orange, because I just think it's kind of interesting. You can kind of see the velocity curve across it if you look closely here. And if I were to zoom in, you can get a little bit more detail. So just a fun coincidence that IC10 was in there. And then we want to look a little closer at these very low velocity clouds. Right, so best thing we can do is plot those over the velocity curve and make sure they fit, right? So here's that original velocity curve we pointed out. Here's that potential cloud out here. And here's the data. So I've just kind of overplotted it on top of this. And luckily we can see that there is kind of some continuity here. So that long strip up there, that's IC10. So we're going to kind of ignore that. But these smaller bits here kind of continue out along the trajectory that we'd expect. So these lines here were kind of the potential predicted paths for this velocity curve after it started moving upwards. And we see it's pretty steep if this is to be trusted, which looking at the data, I think these are from the Magellan extreme, fortunately. So we could continue on this curve out all the way to potentially 160 degrees, a pretty big, massive jump for the length of the stream, an extra 20 degrees of length. And this is just a couple other ways of looking at it. So this is the same plot from before, but then this is Magellanic latitude instead. So again, that's IC10 up there, but all of the candidates for the stream are kind of clustered over in this area, which is interesting. And we're still looking at the various widths that were present in these signals. We're still looking at a few different attributes of these, but we're hoping to put out a paper about this sometime in the coming year. And we're hoping to do some modeling with these new extended lengths. Since this will now put us past the Milky Way midplane in terms of the length of the stream, which is pretty important for modeling these galaxies. Yes, thank you so much. That's going to be it for me.
Interesting. Thank you. Does anybody have questions? I know I have questions. So I'll ask my question first while folks are thinking. So I saw in when you were showing the gas clumps, there were some bits and blobs. Yeah, so that's a good one. But then also here, how did you choose which bits to use and attribute to the stream versus otherwise when you were calculating the curve?
Yeah, so a few things were kind of rolled out here early on as noise. So there's some stuff over here. You can see it kind of follows a straight line. Same thing over here, maybe some residuals from the telescope or some other sort of artifact. So we had to look and kind of sort that out of the data first. The other thing that I've been doing, and this is kind of preliminary, is looking at the various widths and heights to make sure they look realistic and match what we expect from the stream, that they're continuous from the stream and not just some random artifact that's showing up in our data, right? So here's just like longitude, latitude, velocity, and then various widths and heights. So you can kind of see there's some obvious noise that needs to be sorted out. And then more distinct peaks here. That's probably realistic.
Really cool. I'm going to take a
Yeah. That person could take it first since I asked questions already. Oh, sure. Oh, okay. Can you forward one slide, like the next slide? And yes, here. So I thought, great talks, by the way. I thought this slide is really interesting because your new data point is slightly above the white curve. So do you think that's like reflecting like a slightly different inflection curve than what has been proposed based on that clouds on the edge there?
Yeah, that's a great question. Yeah, so I do think that the inflection here is a little bit steeper than maybe previously thought, but both of those lines, there's like a slightly lighter gray dashed line there and then the thicker white one on the bottom. So all of those were pretty probable inflections for this stream, right? And so we're just seeing that within this acceptable kind of realm that we predicted, that inflection point is going. So the actual inflection ended up being somewhere between kind of like the high point for what we thought it could be and this like lower white line, which was what was suggested by this cloud.
And just to add to that, I mean, if there's a steeper inflection point, I think you actually have tremendous amount of implication as to what the CGM of M31 is going to look like, because the current observation has based on mostly the white curve, I believe, but it has a different inflection point that's going to change how the Magellanic string contaminates the M31 CGM. So I thought this is really interesting.
That's awesome. That's a really good observation. I'm really excited to see what people do with that moving forward.
Are there any junior folks who have questions? I want to encourage you to ask.
Kat Barger, Texas Christian University. So at this ending point of the stream, it becomes a lot more like cruddy and banged up, which is not too unsurprising. But and there could be this difference in inflection point. But when I look at this, I'm also thinking that we could gain information about the survivability of the stream as it's traveling through the halo. Now I know it's tricky because we don't actually know the distances and so forth. But have you guys thought about any ways to use this as an anchor of constraint of like gas cloud survivability in the halo?
That's a really good point. I hadn't personally thought about that yet, but moving forward, I think that's a great point. Look at how dispersed this gas is actually getting out there. I love that. Yeah, we'll have to think about that, definitely. Great.
Thank you so much.
Thank you.